of this graph. So this is looks similar, but this is more special graph. So you have here some n-gons with some diagonals, and if you put away these diagonals, you also get a graph class that is called cactus graph or cacti graph. So this is also something that can be characterized in different ways. So here we exclude a k phi minus one edge. Or if we consider trees, then we exclude just K3, because K3 is a cycle of length 3, and if you exclude K3 as a minor, you just get trees. So there are many graph classes that are similar in some sense, but the most prominent one is this graph class of the series parallel graphs. And I also want to point out one property that you might put there. It's a more combinatorial property. You either put some labels to the vertices so that you give them names, say, so from 1 up to n, or you don't put labels. So in this, then you have a labeled version or an unlabeled versions. This makes a difference if you make statistics on the graphs. So the statistics on labeled graphs or unlabeled graphs is slightly different, because if you have labels, then you have less automorphism. So symmetries don't play so much a role if, in contrast to those graphs that are unlabeled. And so unlabeled graphs are more difficult to handle, but in principle, these models are not that far away. And in all these graph classes that I have mentioned, you can consider, of course, the labeled version or the unlabeled version. And the first exercise is to count the number of different graphs that you have if you fix the number of vertices that we call the size of the graph. And it turns out that there is a kind of universality in the asymptotics of the number of these graphs. So, for example, if you consider the labeled case, you have the number of different labeled graphs of size n of this form constant times n to the minus 5 over 2 times the exponential factor times n factorial. So the n factorial clearly comes from the labels, because if you have an unlabeled graph without symmetries, then you have precisely n factorial ways of labeling the vertices. So you have to have this factor here. The exponential growth rate is also quite expected, but what is really nice in this formula is that this sub-exponential factor, n to minus 5 over 2, is always of the same. Of course, the basis of the exponential might change, but this minus 5 over 2 is always the same. And in the unlabeled case, there is no n factorial, but you will have different C and rho, but the form of the formula is always the same. So this has, for example, this was a joint paper where we did this for unlabeled graph. For labeled graphs, this was done before. And there are many possible statistics that you can have on these graphs. If you consider, of course, a proper probability model. And the simplest probability model is a combinatorial one, that you just say that all graphs of the same size. So for example, if you have 1,000 vertices, then you have a bunch of graphs of this size are equally likely. So that this is just a counting thing. So if the probability that the property occurs is just the number of graphs with this property divided by the total number of graphs. So we have a very natural probabilistic model. And if you consider this probabilistic model, then you can consider any parameter as a random variable. For example, the number of edges or the number of vertices of degree 4 or whatever. And I have listed here some statistics that are quite simple. So the number of edges, the number of blocks. I will explain the number of blocks in a minute, and also the number of cut vertices and so on. They all satisfy a central limit theorem with a positive mu, which means that there is a positive proportion, for example, of vertices of degree 4. So you have n vertices and you have u times n vertices of degree 4 typically, where mu is some value, for example, 1/100. So yeah, 1% of the vertices has degree 4, and the deviation of this expected value is then follows the Gaussian law with variance also of size n. So this is quite typical and not unexpected that you have that. And what is also not unexpected, but much more difficult to show, is to get also a subgraph count property that follows a central limit theorem. And this is the theorem that the main theorem that I want to present here, is that if you consider one of these graph classes, so series parallel, outer planar, or cactus graph, or of course also trees, and it turns out many other graph classes, but in particular these graph classes. And if you fix some graph, so for example, cycle of length 4 attached with another cycle of length 3 or whatever, this is a subgraph, and you can count the number, how often such a subgraph occurs. And then you again get that the expected size of this parameter is proportional to n, and the deviation around this expected value follows again a normal law. This is a property that is very well known for many graph classes, for example, for the classical GNP graphs, so the Erdős-Rényi graphs and many others. But for these graphs that are more combinatorial or defined not in a very probabilistic but a more combinatorial way, like this series parallel graphs, this is a new result together with my two co-authors that was published a few years ago. Before I start with the proof techniques that are used here, and I think are of independent interest, at least partly, I want to give you another point of view of these graphs. So all these graph classes that I have mentioned here before, graph classes that look tree-like if you look from a large distance, say. So what does it mean by tree-like? There is a so-called continuum random tree. Maybe you've heard about that. This is a random metric space that is tree-like in the sense that 2 points of this metric space have a unique connection in this space. So this is can be defined formally, but it is the right generalization of a discrete tree to a continuous object. So here you can have not only finitely many vertices, but everything is continuous, and it's also random. So this is a very nice object, the so-called continuum random tree. And the nice thing is that it is a universal limit. So if you have all these graph classes that I mentioned before, including, of course, the trees, so that, and if you scale them by square root n, so that if you, of course, the distance in a graph is just the number of edges that you, the minimum number of edges that you need to connect to vertices. But if you scale it by square root n, or a constant divided by square root n, where this constant is properly chosen, then you get, again, a metric space. And since we have a random graph, we have a random metric space. And we can define on these random metric spaces as a proper notion of convergence. And in this proper notion of convergence, it turns out that these scaled versions of graphs are approximated or tend in this sense to this continuum random tree. So if you look at these graphs from long distance, say, then they all look the same. So you have it, and this is a very nice result, but it's not really what I need, but I just want to show you that how these graphs look like. They look tree-like from the distance. And one nice observation from this is that the typical distance that you can see here in these graphs is of order square root n. So this is true for trees, but this is also true for series parallel graphs and the other graph classes. But now I want to turn to the methods, the proof methods that are used to, or that can be used to obtain this kind of central limit theorem for subgraph counts. And I want to start here with a folklore result on implicit equations. So maybe I start with an example that comes up in tree counting. So there is a very nice method in combinatorics to count trees. So this and the object that you can use here are so-called generating functions. So you maybe know that there are n to the n minus 2 different labeled trees with n vertices. So this is Cayley's theorem. But if you choose one of these vertices as a root, you get precisely n to n minus 1 different rooted labeled trees. And you can put all these numbers together in a generating function. So this means that you take a power series, and the coefficient of this power series is this counting number. Because they are labeled, we divide it by n factorial to make this power series also convergent. And this is the object that you really can use then, because it captures all the information of these numbers. So this is not only the count, it's also not the counting problem for n equals 1, 2, or 3, but for all n at the same time, because it's a generating function where you have the information of all the coefficients together. And why do you use generating functions? The point is that if you decompose an object, and you can decompose a tree by a rooted tree by taking the root, considering the number of subtrees that are attached to this root. And if you look at the subtrees, then there are again rooted labeled trees. So you have a kind of decomposition. You have a root, then you have either no subtree, one subtree, two subtrees, or three subtrees, and so on. And this natural decomposition of a tree can be translated into a functional equation for this generating function. You have either one vertex, so this relates to x. You have either one vertex and one subtree that relates to x times t of x, and so on and so forth, which gives you here, as I mentioned before, a functional equation for this generating function. That these generating functions, t of x equals x times e to t of x. And of course, from this functional equation, you can get back these numbers by evaluating the coefficients. And by the way, there is a very nice method, the so-called Lagrange inversion method, that applies to this functional equation to get explicitly these results. And there is another comment that I want to make, namely that if you here we can analyze this functional equation, t equals x times e to the t, and one observes that there is a singularity at 1 over e. And the local behavior around the singularity is of this form, that the power series converges there, and the local deviation from this value 1 is of a square root form. And this is also reflected by the asymptotics of the coefficients. So coefficients of this generating function is n to n minus 1 divided by n factorial. And if you expand it with the help of Stirling's formula, you get a constant times n to minus 3 over 2, n to minus 3 over 2 times e to the n. And this looks very similar like the formulas from before, where we had n to minus 5 over 2. And clearly this kind of asymptotics directly relates to this square root singularity. And it turns out that this kind of square root singularity is again some universal phenomenon. So you start from a generating a function a of x that satisfies functional equation of this form as we have seen before for the tree case. And under some conditions, I don't want to go too much into the details, then you have always a square root singularity at the radius of convergence. So what are the conditions? Very quickly. So the first condition is that a of x should have non-negative coefficients. As in our tree case, we know that all these numbers are positive or negative because these are counting numbers. And the second assumption is that you can find some point x0, a0, where these two equations are satisfied inside the region of convergence of this function phi. This is no problem in the tree case because here we have just the exponential function, which is an entire function. But in general, it might be different. And then you have to assume that this can be solved. And then you do some kind of local expansion. You have a branch point, a quadratic branch point, and this gives rise to this square root singularity. And if you have the square root singularity, then you also get these asymptotics of this form. And this is, again, universal in this context. Okay, and we have seen this example, and we will see further examples. And there is a very big step now that you can also get this kind of square root singularity in a very general case, namely, even if you have an infinite system of functional equations. Here, in the tree case, we have seen one equation. There will be cases where I have a finite system of equations. But what is interesting is, and that will be used, and this is the main ingredient of the proof, that you have to generalize it to an infinite system of functional equations. But of course, you need some property. And the property that you need is a functional analysis property, namely that if you have to find again some point C0, A0 with this kind of condition. Well, the derivative is now replaced by the spectral radius of the Jacobian. So this is now the right generalization of the property from before, from this property here. And you have to assume another condition, namely that this Jacobian is, well, this is a linear operator, and we assume that this linear operator is compact. Well, this is quite restrictive, or it seems restrictive, but it also turns out that it's quite useful in many applications, as in this application here. And if you assume this condition of the compactness of this Jacobian, you always get a square root singularity. And there is another comment that I want to make, namely that this phenomenon is quite robust in the following sense. If you have an additional parameter in your functional equation, say call it u, then you get this square singularity also uniformly in this parameter u. The only thing is that this singularity will move in u. And another main comment that I want to make is that the condition of the compactness is only necessary if the parameter has some value, some special value. For example, if this value of this parameter is 1, you only have to check compactness if this value u is 1, and this will be important. Okay, how can we use this property of the square root singularity? And how can we use this parameter u in order to get a central limit theorem? This is a very short slide, but it tells more or less that if we have a functional equation with these properties, then we get automatically a central limit theorem. And this functional equation has a combinatorial origin. So if you have this kind of decomposition, then you get automatically a central limit theorem. That is really useful and quite powerful. Why does it apply? So if you have a generating function in 2 variables, so why 2 variables now? So you have a and k is, for example, the number of graphs of size n, where you have k occurrences of a given subgraph. So this k counts the number of subgraphs or number of occurrences of a given subgraph. And if you assume that this function in 2 variables, say it has a square root singularity in the following sense that u is considered as a parameter. So if you put u to 1, you get just so this means that you just sum over all k, which means that you just get the counting generating function for the number of objects of size n. And of course, we have done that before, or we have seen results of that before. Now, if you introduce u, then this is more or less like a parameter that varies around u equals 1, say, and you can do that to get a square root singularity here that varies in u a little. And now you can apply, if you have the square root singularity and you take out the coefficients, you get that the nth coefficients of a of cu then behaves like that. So you have a constant depending on u times rho of u to the minus n, where rho of u is the location of the singularity, times n to minus river 2. And you get this n to minus river 2 universally because it's a square root singularity. And if you take just this simple random model where you just take the number of possible cases divided by all cases as the probability, then the moment generating function or the probability generating function, both are almost the same, of this random variable that you define here is just the nth coefficient of ACU divided by the nth coefficients of AC1. This is just a translation of this simple probabilistic model. And now if you have this asymptotics holds also for the special value 1. And so you can get an asymptotics of the probability generating function. And you see that the probability generating function behaves like the power of a function. And well, if it would be an exact power of some function, then this is just related to a sum of independent random variables. And then if you have a sum of independent random variables, then you get automatically a central limit theorem. This is the classical central limit theorem. And if it is almost a power, an exact power of a function, then you also get a central limit theorem. This is very easy to prove with the help of Levy's theorem. So these are just few lines of calculation. So it's a standard exercises in basic probability theory. If you have a property of that kind, then you automatically get a central limit theorem for the parameter exam. So summing up, if you have a functional equation for your generating function in two variables, you usually get automatically a square root singularity, and from the square root singularity automatically get this property that your probability generating function behaves almost like a power of some function, and therefore you automatically get a central limit theorem. So I call this a probability or a combinatorial central limit theorem, that from a combinatorial decomposition you get more or less automatically a central limit theorem. Well, this automatically is not as automatic as it looks like. You have to do some work, you have to do the combinatorics, and you have to check some conditions. In our case, you have to check, for example, the condition that a proper Jacobian in a proper space is compact. Okay, well, I cannot give you all the details, but let me give you a flavor of how you can use this concept for series parallel graphs. So first you have to count series parallel graphs, and this is done with the help of generating functions. And here we start with generating functions in a number of vertices and edges. So this is just this is necessary for doing the combinatorics. And here we see some equations for these generating functions that are just replacements of the serial parallel extension. So here we have a series network, here we have a parallel network, and this decomposes in the series. You get a series of networks, and here you get some parallel networks of series networks. And so this is just the definition, more or less. And from the network, you can get the two-connected version by just selecting one edge. Therefore, you need the edges. But the core of this combinatorial decomposition is this equation here that I want to explain a little. And what does it mean? So it's related to the so-called block decomposition. So if you have a graph like this, by the way, this is a series parallel graph, and you have some so-called cut points. So cut points are points where when you put them away, then you disconnect the graphs. So this is a cut point, because if you put this away, the graph is not connected anymore. This is not a cut point, because if you put it away, the graph will be still connected. But if you look at what remains, if you just look into the paths that are in between the cut points, you will see so-called two-connected graphs. These are the blocks. So here you see the blocks of this graph, and this is the block decomposition. Blocks are two-connected. Two-connected means that you have to remove at least two vertices to disconnect. But you can view it also the other way around, that you can start with the two-connected graphs of your class and put them together by introducing some cut points. And this is the way of doing. So this equation that we have seen before relates the generating function of the two connected graphs with the connected graphs with this block decomposition. Well, to make this unique, you have to start with a marked vertex or a root, and then you have a tree-like decomposition. And this tree-like composition just translates into a functional equation that looks very similar as the functional equation that we had for trees. For trees, the blocks are just edges. So this is a special case for this general equation that we have. And you can also do it with edges and so on. And there is one nice point, namely that in many cases, we can solve these equations inside the region of convergence, and then we automatically get a squared singularity. And if this is doable, we need this graph class subcritical. And in particular, if this condition is satisfied, this follows from the calculations that the second derivative of radius of convergence of the two connected generating function times eta is bigger than 1, then we are in the subcritical case. And this is in particular the case when the second derivative goes to infinity. And in our case, we have the property that the generating function of the two connected graphs, and the two connected graphs we can see here, they will have a squared singularity that comes from this system, more or less. And so we are in the subcritical case. And if we are in the subcritical case, as we are in for serial parallel graphs and all the other graphs, then we get very easily these asymptotics. And I just want to give you a hint of why we get that. So if one equation, we get a squared singularity from this equation, and here we have the pointed connected case. So we have n possibilities to point this. So we get from this asymptotics n to minus 3/2. If we put away this pointed vertex, and we have to divide by n and get n to minus 5/2. So this is more or less the reason for this asymptotics. Maybe I go quickly to the final form that has to be done to count subgraphs in series parallel graphs. The problem is that you have to find some combinatorics for or recurrence relations for the generating function, where you take into account these subgraph counts. And it turns out that you cannot put this into one equation. If you put it into one equation, then we are in a very simple situation. Maybe I go back to that. For example, if we count edges, then we have one equation and we get directly a central limit theorem. Or if we count two connected components, then we have one equation and we get a central limit theorem automatically, because this block decomposition is just one equation, and we can put things together easily. The problem if we count subgraph is that a subgraph can be can be in two different blocks, and if it's in two different blocks, then we have many different situations that have to be considered. And what can be done is that we really have to consider infinitely many situations and get then infinitely many equations for the generating functions of connected series parallel graphs, where x counts the number of vertices, u counts the number of appearances of a proper subgraph. Here, this is just the equation if we count subgraphs that consist of just two edges attached together, so a path of length 2. And here we have, the problem is that we have here, if we are in different components, where we have a cut vertex that has degree J1 in one component and degree J2 in the second component, then we have J1 times J2 new appearances in addition to the other appearances. So we have really an infinite system of equations. But, and this is another point, is that if we put this variable u to 1, all these equations collapse into a single equation again if we sum up. And this is actually the reason why the Jacobian in this case is compact. So we are in lucky situation. we get this compactness of this operator for free. So the only difficult part here is to reformulate our counting problem, or the number to count the number of occurrences of a given subgraph, translate this into a proper generating function, or as in this case, to a system of functional equations for this generating function. And here we really have to do it for infinity cases. And here we see why we have to have infinity cases, because we have to distinguish between the degree of the root vertex, of this marked vertex. So there are infinitely many cases, and this J really gets into the play as we look at into the equations, and so this cannot be avoided. So summing up, point is to get some combinatorial decompositions. Here in this case, this combinatorial composition is just this block decomposition that can be made unique by taking a rooted vertex, and then we have blocks and attached with again rooted versions and so on. So this is just a tree-like recurrence. And we have to make this more precise when we count some additional properties. Counting edges is very simple because there are no overlaps. But if we have a subgraph that might overlap between two or even more two connected components, and so we have to take these different all these situations into account, and this gives rise to an infinite system of equations. This infinite system of equations, if the Jacobian is compact, leads to a square root singularity, and as I have explained before, if you have the square root singularity, then you automatically get the central limit theorem. So let's go back to the theorem. So, and this is the theorem that we have. If we have a so-called subcritical graph class, series paragraphs, autoplanar graphs, and so on are all subcritical graph classes. They all look tree-like, which means that the two connected components are not very big. If you look from distance, so this is a universal property. So we have a scaling limit. It's a continuum random tree, and we have very precise results on this counts, that number of edges, number of blocks, number of cut points, but also if we count the occurrences of a given subgraph. And thank you very much for your attention.
Thank you, Professor Drmota, for this nice talk.
Thank you.
Are there some questions?
Yeah.
Yes. Okay. In this slide, the coefficient mu, how it depends on the subgraph H. The constant mu here.
So I'm sorry, I could not hear the first part of your question. So you have the subgraph H, yes?
And you have some constant mu.
Yes. Yes, these constants mu and sigma that define the Gaussian law, they heavily depend on the subgraph H. So you fix a subgraph H, and then there exists some constants mu and sigma with the central limit zero.
Okay.
Yes, of course, they heavily depend on the subgraph.
It depends on the size or on the form of H.
It really depend on the form of H. Actually, it's not easy to compute them. So there are only very special cases where you can compute them. So the problem is that you have this infinite system of equations. So if it would be a finite system, then you could solve, or you could calculate them at least approximately. For the infinite system, you just get some relation that has to be satisfied for that. You know they exist, but only in very few cases you have them explicitly.
Okay. And how would you find the diameter of the graph? What is the diameter? DN?
The diameter. Okay, so this is a very nice thing. So if you have this, where is it? So if you have the scaling limit here, well, if you divide by square root n, you have a limiting object, and the limiting object has a finite diameter, and so this is a weak limit, and the diameter is a continuous functional. So this means if from this weak limit, you also get a weak limit for the diameter because it's a continuous functional, and therefore you get that the diameter will be, yes, is just scaled by square root n and has a limiting distribution.
Okay. Okay. Some other questions, please.
Oh.
Other questions?
Yes, please.
Yes, please.
Salam, good afternoon. Thank you, Professor, for the nice presentation. Thanks, Dr. Nabil, for organizing this. In one of the slides, you presented the Tx equal to x multiplied by e Tx, yes?
Can
you hear me? Or?
Yes. I think it was the tree case.
Yes, the tree case, yeah, the continuous tree case, yes. And I think if you look at the log, the ln of both sides, then it would be like ln x would be Tx plus x, yes?
Why I'm just, is this e here?
I'm not, okay, then maybe I should put the screen.
So
yes. If we look at it on the ln side, yeah, okay, when you wrote it, yes, of course. So if you take the ln of both sides, the natural log of both sides, then you'll get that ln Tx would be equal to x to ln x to x plus to Tx plus ln x.
Maybe I should be, I'm not sure if we speak of the same thing. So 1 over e is just the singularity. So and this is just x divided by x0. So e is 1 over e is the singularity. So if x equals 1 over e, then this gets 0 and you have a branch point, a quadratic branch point.
Yeah, you are absolutely right. But what I'm talking about is if we look at the same equation, but we take the natural log of both sides.
Yes.
Then you would get something like ln of Tx would be equal to ln of x plus Tx.
Yes.
Okay. So Tx could be looked at as ln of itself minus ln of x.
Yeah. Yes.
Okay.
That's the same.
Yeah. Or yes. Okay. So that so this is kind of a very interesting relation in the sense that perhaps one could look at the entropy of this kind of equation, or this kind of the Tx in this sense, because of this special relations. And I'm personally interested in applications of the Sumudu transform. The Sumudu transform basically is somewhat a derivative of the Laplace transform, although it has stronger properties, including maybe applications to probability theory and generating functions, as you have done here. And if we, the ln of x, for example, in the Sumudu transform, the transformation of ln of x would be ln of x ln of u minus gamma. The gamma would be the Euler number, the Euler number that is 0.56 something. The Euler number. So it is really a very interesting property. So I think there is a very strong relation, perhaps, with this and with the number gamma, the Euler number gamma.
Well, you see that this function is a very classical function. So maybe you know the Lambert function. So this is, well, yeah. It's up to a constant or -1, I think the Lambert function.
Yeah.
Very well studied. I am not sure that the Euler constant is involved directly with that, but there's so many properties of this function. So maybe, if you can, maybe you can send me some email and then I can answer more precisely on that. So
it'd be great. It'd be great. I've already left my email. It's the first chat. When I said hi to everyone, I put my email in there. My name is Fethi. I'm from Tunisia, like Professor Nabil, and I'll be happy to communicate with you.
So please send me an email, and then I will try to reply as soon as possible to answer your questions.
No problem. Thanks for a very nice lecture. Thank you very much.
You're welcome. Thank you.
Thank you, Dr. Fethi, for your questions.
Thank you.
I have a question. What are the tools you use to extract the coefficient of xn in your series in general? You use complex integral or what?
I'm sorry, I could not hear. Could you do it again? I thought that the audio was not fine for me.
The tool that you use to extract the coefficient of x to the power n in general in your series. Yeah.
I am sorry, I cannot hear you well.
Okay, it's clear now. Okay, you hear me?
I hear you, but it's that the connection is not very good from your side, I think.
Rafiq, your microphone is not.
Not good.
No.
Okay. No problem. Are there other questions, please?
Yes, I could ask one.
Yes.
Hi, Michel. Thank you for a very nice lecture. I was wondering if you could obtain the joint normal distribution for an infinite class of natural graph of I don't know, like.
So what you will certainly get is a joint central limit theorem for two subgraphs and so on, or three. So for a finite number of subgraphs.
Yes. But if you have an infinite number.
No, I don't think so. And there is a simple reason. So what we are using is that if you have a fixed subgraph, then you have, well, a finite diameter of that, and then this means that it will affect only finitely many blocks, and this is important, at least from what I have now. So I don't think that you can do everything to the infinite, but a finite number is certainly doable.
Okay, thank you.
You will lose. I'm not sure that you will. Well, you might lose the compactness of the operator for infinitely many, but for finitely many, you will have the compactness for sure. Yeah. There might be a theorem for infinitely many, but I don't know at the moment how to get it.
Yeah, it looks difficult.
Okay, thank you, Nicola, for your question. Other questions, please? Other questions? So, if no other questions, you send me the slides to put them in our website after this talk.
Sorry.